Hello friends, welcome back to our channel Concept with Clarity 1. In this lecture we are going to discuss about the logic gates and the associated graphs with the logic gates. So we'll start this lecture series digital electronics. So in this lecture series, like what we are going to see is, we all know digital electronics is all about implementing any Boolean function by using, you see here, digital electronics is all about implementing any Boolean function by using logic gates, universal gates, multiplexer, decoder, ROM, PLA, PAL, PLDs, CPLDs, FPGAs and ASICs. Okay, so from starting to, we start our discussion with the logic gates. Those are the basic building blocks of digital electronics. And what is we study in digital electronics is, digital electronics is all about implementing the Boolean function by using either logic gates, either universal gates, multiplexer, decoder, ROM, PLA, PAL, PLDs, programmable logic devices, CPLDs, right? PLA means programmable logic array and PAL means programmable array logics, CPLDs, FPGAs and ASICs, right? So here we use coding, either Verilog or VHDL code. The hardware is readily available, so we'll be using the coding, right? So in this we are going to study about the logic gates in this lecture. Okay, so what are logic gates? What are logic gates is, see here, in the analog electronics, if I take in analog electronics, what are the basic building devices? What are the basic devices in analog electronics are, one is diode, two is transistor, and the third one are FETs, correct? So you study about diodes and the circuits constructed by using diodes, you study about the transistors and the circuits constructed by using the transistors, and you study about the FETs and the circuits constructed by using the FETs in the analog electronics. So what about digital electronics? In digital electronics, okay, the basic building blocks or basic building devices are logic gates, only logic gates. Okay, rest of all the circuits are made up of logic gates only internally. Even if you take a multiplexer, again it's a combination of logic gates. Even if you take a decoder, again it's a combination of logic gates internally, right? So the basic building devices in the digital electronics is logic gates, and the circuits constructed by using the logic gates we are going to study, like multiplexer is a circuit, decoder is a circuit, comparator is a circuit, right? Multiplier is a circuit, adder, subtractor and many more, right? So in digital electronics, logic gates are the basic building blocks, right? Now what is logic gate, right? Logic gate is nothing but it implements some kind of logic, okay, the desired logic. Okay, in the intermediate, in the schoolings we have studied, like there will be two switches in series, two switches in parallel, right? Two switches in series connected in series, okay, switch 1, switch 2, correct. So if I give an input here, this is the input and this is the output, right. If I give an input here, then for suppose I get an output only when two switches are, that is short circuit, that means on, right. So only I get an output when two inputs are on, that means it is simply an OR gate, right. Similarly, if I connect in parallel, that will be an AND gate, right. So it is implementing some desired logic, right. So we'll see the types of logic gates available. First one, NOT gate. Second one, AND gate. Third one, OR gate. Fourth one, NAND gate. Fifth one, NOR gate. Sixth, exclusive OR gate. And seventh, exclusive NOR gate, okay. And NOT gate, AND gate, OR, NAND, NOR, XOR and XNOR, out of which NOT gate, AND gate, OR gate are called our basic gates, okay. These are called as basic gates, right. The other gates are just NAND is the complementary AND plus inverter, combination of both AND and inverter is NOT gate, right. Sorry, and NOT gate is NAND gate, okay. So we'll start our discussion with NOT gate, okay, and the associated graph with it. What is a NOT gate? The symbol for a NOT gate is simply an inverter, okay. What is an inverter, right? So if I give input A, then my input will be A bar. What is A? A can have value either 0 or 1, right. See, in digital electronics we talk about only 0 or 1. 0 means ground and 1 is nothing but plus VDD, okay, that is plus 5 volts. 0 means 0 volts and 1 means plus 5 volts, correct. So that is why I am taking the A as the input, where A can have either 0 or 1. So if I give A as the input, then A bar will be my output, correct. So that is a NOT gate. If I see the truth table, A and A bar, okay, if A is equals to 0, then I get output as 1 for A bar. If A is equals to 1, then the output here it is 0, okay. So that means complementary inputs. Let us see the graph for this, okay. So how is the graph in the digital electronics? That will be in the form of either 0 or 1. Let us take my graph A as like this, okay. Whatever the pulse you can take in the form of a square, where this one represents 0 and this one represents 1. This is 0, this is 1, okay. I am taking a simple graph, right. So what will be my A bar? A bar will be, it will be 1, 0, and whenever the input is 0, output will be equal to 1, and this will be this thing, okay. So this is 1 0 1 0, this is the output for the NOT gate, okay. So whatever the input I give, the complementary of the input will be my output. Now we shall see AND gate. So what is AND gate? The symbol for this logic gate is this one, okay. So if I give A and B as the input, I get A into B as the output, okay. Like as I said, A and B can have both either 0 or 1, okay. So let us have the truth table. What is the truth table? A, B, let us take Y. Y is equals to A into B, okay, that is equal to A into B. So A can have either 0 0, either 0 1, 1 0 or 1 1 values. Maximum 2 inputs means 4 combinations I can get, Okay, so what is this one? Y is equals to A into B. A into B means whatever the inputs I have, the multiplication of the inputs is my output. 0 into 0 is 0, 0 into 1 is 0, 1 into 0 is 0, and 1 into 1 is 1, correct. So this is the truth table for AND gate. So the associated graph I can draw like this. Okay, so the associated graph, you see here, what is A? 0, 0, 1 and 1. You can see here 0, 0, 1, 1 for A, right. Next, what is B? B is 0, 1, 0, 1. Okay, so this is 0 and 1, this is 0 and 1, right. So and again let me tell you where I can draw these graphs is I can use any simulation tool like Model Sim I can use, or Xilinx I can use, and there I can write a program, and when I simulate, the graphs will be in this form only. Okay, you can see this as Model Sim simulator or Xilinx, different Xilinx. So in these simulators you can see the graphs, you can write the code for an AND gate and you can visualize the graphs. Okay, there, right. So you see here, what is my output? Output Y is equals to, what is my Y? Multiplication of the inputs. 0, 0, 0 into 0 is 0. This is 0, 1. 0 into 1 is 0. Okay, 1, 0. Again I get an 0 output, right. And 1 and 1. When I multiply both inputs 1 and 1, then I get an output 1. So this is the associated graph for an AND gate. Okay, so when to get an output 1 in the AND gate, right, both the inputs should be equal to 1, then only I get an output equal to 1 in the AND gate. Similarly, I can have an OR gate. What is an OR gate? The symbol is like this. This is an OR gate. Okay, A, B. What is this one? Logic is A plus B. Okay, so addition of two inputs, right. So my truth table goes like this: A, B, Y is equals to A plus B. Okay, I can have the inputs 0, 0, 0, 1, 1, 0 and 1, 1 as the inputs. So what is this one? This is the addition. 0, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is also 1 for an OR gate. Okay, in digital electronics we don't have any numbers apart from 0 and 1. Like in binary number system we have only 0 and 1. 1 plus 1 is equal to 1, not 2. Okay, so in binary we have numbers called as 0 and 1. The maximum number will be 1 only, right, when I add for an OR gate. Okay, so arithmetic addition is different, and for an OR gate the logic is when the inputs are 1 and 1, the output will be equal to 1, right. So what is the graph? You can see the graph here. You can see the graph. So what is my A? A is 0, 0, 1 and 1, correct. 0, 0, 1, 1. What is my B? 0, 1, 0 and 1. 0, 1, 0, 1. Okay, what will be my output? My output will be Y is equals to A plus B. Okay, 0 plus 0 is 0, 0 plus 1 is 1, and 1 plus 0 is 1, and 1 plus 1 is also 1. Okay, this is 0, 1, 1, 1. So 0, 1, 1 is my output for an OR gate. Okay, and we have another gate called as NAND gate. The gates NAND gate and NOR gate are called as universal gates, right. So why we call them as universal gates is any Boolean function can be implemented by using universal gates also. Okay, universal gates means by using NAND and NOR gates, right. So any Boolean function can also be implemented only by using NAND gates or only by using NOR gates, right. So let us say if my design is having 100 gates. Okay, if I wanted to connect 100 different types of gates, if I wanted to connect each and every gate, there I can make a mistake, or else in the universal gate design means all the 100 gates will be NAND gates only, right. So that will be easier, right. So that we will discuss later. But what is NAND gate is, NAND gate, it is AND gate plus inverter, right? So this is AND gate, and then I have an inverter here. Okay, so A, B, right? If A, B is my input, then this will be A into B whole bar. Okay, A into B whole bar is my output. Okay, so what is the truth table? A, B, A into B whole bar. Okay, 0 0 0 1 1 0 1 1, right? So you can see here what is the NAND gate. A into B, multiplication of the inputs and the complement of these. So 0 into 0 is 0, so the output will be equal to 1. 0 into 1 is 0, so the output will be equal to again 1. 1 into 0 is 0, the output will be 1. 1 into 1 will be equal to 0. Okay, so this is the truth table for a NAND gate, right? So the associated graph I will show here. So you can see A is 0 0 1 1, B is 0 1 0 and 1, right? So 0 0 1 1 0 1 0 1, correct? So what is my output? My output is nothing but, my output is Y is equals to A into B whole bar, that is 0 into 0. So I can directly draw 1 1 1 0, right? So this will be equal to 1 1 1 and 0, 1 1 1 and 0. Okay, so this is the NAND gate. Okay, similarly I can have a NOR gate as well. NOR gate means OR gate plus inverter plus a bubble. Okay, so this is A, B, A plus B whole bar. The truth table is A, B, A plus B whole bar, 0 0 0 1 1 0 1 1. When I add two zeros, the output is 0, so I am having a bar, so that the output will be equal to 1. So the rest of the output 0 plus 1 1 0 and 1 1, the outputs will be equal to 0. Okay, so the graph of NOR gate is like this: A 0 0 1 and 1, B is 0 1 0 1. Okay, so 0 0 1 1 0 1 0 1. So the output will be equal to A plus B whole bar, that will be equal to 1 triple 0. Okay, 1 triple 0. This is the graph, right? Similarly I can have exclusive OR gate. So what is exclusive OR gate? Is exclusive OR gate, the output for an XOR gate is 1 when I have odd number of ones in the inputs. That means if I have odd number of ones in the input, then the output will be equal to 1. That is the logic of XOR gate. Okay, so exclusive OR gate, the symbol is shown like this. This is an exclusive OR gate where my inputs are A and B. My output is nothing but A XOR B. A XOR B is written as A bar B plus A B bar. Okay, this is the notation, right? A bar B plus A B bar. How we have written this one also I will tell you. So let me write the truth table: A B, A XOR B, right? So 0 0 0 1 1 0 1 1. Okay, so see here, whenever there are odd number of inputs, here I don't have odd number of inputs, so the output equal to 0. 0 and 1, here I have the odd number 1 1 1, so odd number of input, the output will be equal to 1. Here the output will be equal to 1. 1 and 1, the output will be equal to 0. Okay, you can see here I have an output Y is equals to 1, Y is equals to 1 and 1 whenever the inputs are A B. The combination is, one is A is 0 and B is equal to 1, A bar B and A B bar. At that time only I have 1, so I add. That is the equation derivation for an XOR gate. That means wherever I have a 1, I need to write the input combination and then I need to add. That will be my output equation. Okay, that is how you need to derive. Okay, please remember. So the associated graph I can draw here. So this is 0 0 1 and 1, and this is 0 1 0 1. Okay, So 0 0 1 1 0 1 0 1. So this is A, this is B. So what will be my A XOR B? A XOR B is nothing but 0 1 1 0 0 1 1 0, right? So this is the associated graph for your XOR gate. Similarly, I can have exclusive NOR gate. Okay, what is exclusive NOR gate? XOR gate plus inverter, right? So if I have A B here, this is A XOR B whole bar. The A XOR B whole bar, this can also be written as A XNOR of B, circle and a dot in this. Okay, and the equation for this will be AB plus A bar B bar. That also we'll see. So this is A B A XNOR of B. This is circle dot, right? 0 0 0 1 1 0 1 1. It is the complement of the XOR gate. So this will be 1 0 0 1, right? So like I told you, wherever I have a 1, here I have a 1, the input combination is A bar B bar, and here I have 1, the input combination is AB. So that is how you write the equation, right? And the associated graph with for this you can draw, I feel, 0 0 1 and 1 and 0 1 0 1. Okay, this is A B, and the associated graph is 1 0 0 and 1. Okay, A XNOR of B, 0 0 1 1 0 1 0 1. So 1 0 0 1. Okay, hopefully I expect you people that you have understood the concept of logic gates and the associated graphs with it. So if you understood the concept, please like the video, share and subscribe the channel, and in the coming lectures we'll move forward with the digital electronics other topics. Okay, thank you for watching. Bye.